In this video, we're going to look at some igneous processes. What's happening to the magma in the magma chamber? How do we even get that magma in the first place? We're going to start with looking at how to melt a rock. All right, because it's not as easy as it sounds. So melting is going to happen right at the core mantle boundary for the most part. All right, so the easiest way to melt it is to heat it up. Right? So the geothermal gradient tells us how hot the earth is. If you can get it down below that gradient, you can heat it up. Right? But in the mantle, that's really, really hard to do because, remember, the pressure is really high and it keeps it from being able to melt. So a liquidus, this is a line where how hot you would have to get it to be able to melt. This is the geotherm, which is how hot it actually is. So that gap in the between is why that mantle stays a solid. But one easy way to melt a rock is rocks will melt due to rising plutons or diapirs. Right? This is generally not the case in the mantle to get the mantle to melt, but it does occur in the continental crust due to igneous intrusions into that granite. So in this case, you've got basaltic magma, and basaltic magma is really hot. It's one of those higher temperatures because it's all the stuff higher up on Bowen's reaction series. Its melting temperature is actually higher than the melting temperature of granite. So as that basalt intrudes into the granite, it starts to melt out the stuff at the bottom of Bowen's reaction series because they melt at the lowest temperatures. So you're going to start to melt quartz and muscovite and potassium feldspar. And then in that case, that melt is really, really felsic. All right, and you get rhyolite magmas that way. One of the big, easy ways to melt the crust is by reducing the pressure. Because if you reduce the pressure, then the rocks in the mantle are actually able to melt. So you can have a hot spot. So a hot spot starts really hot down deep inside the earth, and it rises really fast because it's hot. And since it's that hot, it's actually able to melt through the crust. If you have a divergent plate boundary, like a continental rift, you're pulling those plates away from each other, that's going to thin the crust. And when the crust thins, you get decompression melting there. The other place is going to be at the mid-ocean ridges, and it's basically the exact same process between those two. You can also introduce volatiles, and we talked about this in terms of plate tectonics. So volatiles, like water, like carbon dioxide, that's being released from the crust, either in water that seeped in or water that's part of the minerals. Once they're heated up down in the deep mantle, in the top of the mantle, those tend to lower the melting point of the mantle. So as those mix in, the mantle starts melting here too. So we can look at a graph of what that actually means. So over here, this is a melting curve for granite. So this is dry granite. So when granite's really dry at the surface, it's going to melt at, 750-ish degrees Celsius? And then as you go deeper and deeper into the crust, you have to get it hotter and hotter and hotter to melt it. But if you get it wet, the deeper you go, actually the easier it is to melt it, at least down to like 650 degrees or so. So you can see that actually lowers the melting temperature considerably in that case. Now, of course, these all are connected to the plate tectonic settings. So the settings where you get volcanoes, which means where you get melting. If we look at a map of where the volcanoes are, they're all over the earth, but there's some definite locations they're mostly at. So divergent boundaries are going to have melting because of decompression melting. Subduction zones are going to have melting because of the volatiles being introduced. And hot spots, this is really a question of pressure as well. So hot spots, subduction zones, divergent plate boundaries. Those are the big tectonic locations you're going to get melting at. Right? So why don't you get it melting at a continental collision? Well, if you think about it, when two continents collide, the crust tends to get thicker. And that makes it even harder for the mantle to melt. At a transform plate boundary, You're not actually introducing anything into the mantle. You're not thinning the crust anyway, so you don't have our major ways of making it melt there. So let's think about this, though, because at the plate boundaries, what's actually melting to make the magma? If we look back here, it's always right there at the very bottom of the crust is where the melting is really occurring most of the time. All right, so the very bottom of the crust, very top part of the mantle. There you see. So very top of the mantle, kind of very top to the middle part of the mantle there. And pooling in here. So if the mantle is what's melting, what is the mantle made of? It has an ultramafic composition. But how much ultramafic rock is actually being erupted in volcanoes? Absolutely none. So what does that mean in this case? How do you get a felsic lava if you're melting ultramafic rocks? All right, there's a few ways to do this. We talked a little bit about this in one of the classes. So on Bowen's reaction series, what mineral is going to be melting first once you start heating it up? We pull this up. The very first minerals to melt is going to be quartz, and then muscovite, and then potassium feldspar. So if you have a rock that if you have a already felsic rock that you start heating up, those are the first things that are coming out of it. So that's what the lava is going to be enriched in. But if you look at this, an ultramafic rock has amphibole and pyroxene and plagioclase and olivine. The olivine doesn't want to melt, but the amphibole and the pyroxenes will. So the first mineral that forms in Bowen's reaction series is that olivine. All right. So if the olivine forms in a magma body, or the pyroxenes, since the olivine is not going to want to melt very much at all. So you're forming olivines, you're forming pyroxenes. They cool, but then if they're solid, they're more dense than the magma body they're in, so they sink down to the bottom. This is called crystal settling. And as those settle down now, you've got less iron and magnesium in your magma. And then the next type of mineral forms, and it starts crystallizing and settling down at the bottom. And so in this case, you have a melt that's got very, very little iron, very, very little magnesium. So you've got more of an intermediate or closer to a felsic magma now. And this is kind of cool. There's one place on Earth in the Palisade Sill that you can actually see this. So the Palisade Sill, we've talked about what a sill is, right? And you can see here it goes up along just west of Manhattan Island and through Staten Island and on its way up here, up the river. That's a picture of it. If you look at the chemistry of the sill, at the very bottom of it is all olivines and pyroxenes. Then you have plagin pyroxene. Then you have plagin amphibole. So it's kind of cool. You can actually see that settling out, sort of. All right, but the crystal settling doesn't create much lava that's felsic in composition. And felsic plutons are the most common type of pluton. So how else are you going to get a felsic lava? Well, let's think about this. What is the continental crust made of? Granite. And what's the composition of granite? It's made of quartz and potassium feldspar and a little bit of biotite, a little bit of plage, a little bit of muscovite. And so granite is actually melting at a much lower temperature than basalt. And so we can do this process of assimilation, just like the Borg. Right, so as magma goes into country rock, it actually starts melting the rocks around it. So it melts the rocks and then incorporates it in. So this sandstone probably has lots of quartz in it. That starts to melt and you add it to the magma. And so the magma now is a little bit more felsic, a little bit closer in chemistry to the surrounding rock. Sometimes you have chunks of material that is in the lava that just never melts. Maybe its melting temperature was a little bit higher. Maybe it was insulated